Hello, welcome back to Engineering 201 Electrical Fundamentals, and we're going to pick up where we left off last time, continuing our work in Thevenin's theorem and Norton's, which the difference between Thevenin and Norton is just a source transformation. And that brings us then to the subject of maximum power transfer. When we left off last time, we alluded to this, that if you took this Thevenin model, which you could represent any circuit as a Thevenin model, and were to apply a load resistor across here, we'll call this R sub L for load, so we have voltage Thevenin, which would be the same as voltage open circuit, and our R Thevenin, which is the ratio of our short circuit current to, our Thevenin would be V open circuit divided by I short circuit, or you could use the shortcut to get it if you didn't have any dependent sources. Is that right? Yeah, because that's really just a statement of Ohm's law. We've got V is equal to IR, so R is going to be V over I. Yep, absolutely. So that's where those come from. And anyway, back over here to this load resistor, R sub L, you could imagine if the resistance is too great, this current through here, if we talk about this current, and I call this current I, if the resistance is too great, then I will be small, although if the resistance is too small, then the voltage across here, this voltage across here, will be too small. And I won't put a label in there. I don't want to confuse that. But that's what we're up against. This resistor has to be just right. If it's too small, one of the values is off. If it's too large, another one of the values is off. So looking at power being, and I guess we'll put it up here with Ohm's law, power being equal to current times voltage. How do I select just the right resistor, like Goldilocks and her porridge, not too small and not too large, or not too hot and not too cold, to transfer maximum power? Well, that's our task for today. So I'm going to say then that the power, and I'm going to, having combined these two, say that the power is equal to I squared times the resistance, and I will use R sub L for that. And I'm going to make some substitutions on this. We could, of course, if we take the total voltage here, which would be V Thevenin, and divide that by the total resistance, R Thevenin plus RL. If I take and square that, that's the current, and then I just multiply it by RL. And again, backing up, of course, when you combine these, you get power is equal to I squared times R in general. These are all general. And then applying them to our particular situation, taking that I squared and this current here, squaring it, and multiplying it by the load resistor, I get the power that's being dissipated there in that load resistor. I make the substitution for I, which is going to be V over the total resistance, and then I still have R sub L there. And we notice a few things here. We notice that V Thevenin and R Thevenin, those are going to be fixed. So we can say then that maximum power is then a function of RL. So let me rearrange this a little bit, and rearranging this expression here, we could say that power is equal to V Thevenin squared, bring that outside, and then I'll look at this term, because that essentially is a constant. We recognize that as fixed. And then I've got this term RL, it's not squared, divided by R Thevenin plus RL. That is squared. Is that right? Yes, that's good. So what we'd like to do then is, and that's a squared, not equal to, there we go, squared. Anytime we think about minimum and maximum, we probably think about Math 251, taking a derivative. So let's go ahead and do that. I could say to find the maximum, I'm going to set the derivative equal to 0. That is, I'm going to set 0 equal to the derivative of the power with respect to the value of the load resistor. Okay, and you might say, well, when you take the first derivative, you don't necessarily know whether it's a minimum or a maximum. That's true. We need to take the second derivative and look at how that behaves, or we could take the first derivative and graph it. That's what I'll do and deal with that. And we will find out that indeed it is a maximum. So I don't want to overlook that, but we will address it. So looking at this, we really have a constant times a quotient, right? We have a constant times a quotient. So I'll go ahead and dealing with that, I'll look at the constant. So I have V Thevenin squared, and then I'm going to use the quotient rule. So I'll go back to calculus and use my quotient rule, where I have the denominator, which is R Thevenin plus RL squared, times the derivative of the numerator. What's the numerator? R sub L, so the derivative of that is 1, minus then the numerator, so that's R sub L, times the derivative of the denominator. Well, the derivative of the denominator, I have to use the chain rule, so that's going to be 2 times R sub Thevenin plus R sub L taken to the first power, right? Okay. And then the quotient rule requires me to take the denominator and square it. So when I square something that's already squared, I get it to the fourth power. So I've got something like that. So again, I've got a constant here times a quotient. Go through the calculus on that. Now, setting that equal to 0, multiply both sides by the denominator, divide both sides by the constant, and I come up then with 0 is equal to R Thevenin plus RL squared. And let's see, that 1, I'll have to subtract off 2 times RL times R Thevenin plus RL. We could move 1 to the other side and get rid of the negative sign, and then I have this term. Let's say I put this term over here, that would be negative. I get to cancel a negative, so I could square that out. So I'm going to say that I have R Thevenin squared plus 2 R Thevenin times RL plus RL squared is equal to this side over here, and because I moved that over, they both had a negative, so I dropped the negatives. I could just say that this is 2 RL R Thevenin plus 2 RL squared, right? So then what do I get? 2 R Thevenin RL, I've got that on each side, and I'm left then with R Thevenin squared is equal to, I subtract that from those over there, and I have RL squared, and I get that R Thevenin is equal to RL. That is, and that's worth probably a box. That is for maximum power transfer. Okay, so if someone wants to know what resistance they can put on a circuit to get maximum power transfer, what you can do is come up with a Thevenin model. Once you have the Thevenin model, then you know that if you put the load resistor on having the same value as the Thevenin resistance, you'll get that maximum power transfer. The resistance won't be too large, the resistance won't be too small. Okay, so with that, you could actually go back and, let's say, look at this expression here. If you came back and substituted into that, or for that matter, this one, and recognizing then that R Thevenin is equal to RL, you could say then that power maximum is equal to V Thevenin squared times RL divided by, what are we going to get? If those are the same, that would be just essentially 2RL. And when you square that, when you square 2RL, you get, maybe I'll do this 2 times RL squared, so you get let's see, 4 RL squared, and you get to cancel that, so you have then V Thevenin squared. The RL you cancel with one of those, but you do have the 4 in there for RL. And a lot of people will write that equation down and keep that one. I usually don't. Life's too short to try and remember things like that because it's so easy once you have the Thevenin model to figure out what the power is going to be. You don't necessarily have to remember something like that. Let me show you. So we said that if you took the Thevenin voltage and you had the Thevenin resistance, for maximum power transfer you would need to put RL equal to R Thevenin, right? So what's the voltage across here? That voltage across there, V, is equal to, because these are the same, it's a voltage drop. It's going to be even. Half the voltage there and half the voltage there. So that's V Thevenin divided by 2, right? So we could use our old friend that power is equal to V squared divided by R. So what am I going to have here? V Thevenin over 2 squared divided by R. We'll use RL. And this turns out to be V Thevenin squared. Let's see, we've got then 4, because that's 2 squared, times RL. Does that look like that one right there? Yeah, it does. V Thevenin squared, 4RL. So, like I said, I don't try and remember things like that when they are so easy to deduce from the model. Now, one thing that we probably should do, let me double check that. I think we're good with that. One thing that we probably should do is address that, well, really, is it a minimum or is it a maximum, like a good calculus student would? And if you go through this and graph it and look at different values of, so you come back and talk about graphing the expression V Thevenin squared times RL divided by R Thevenin plus RL squared. If you look at graphing that, make sure I got that right, yeah, over RL, you'll find a graph that looks something like this, where it comes up to a maximum value here, and that maximum value hits when RL is equal to R Thevenin, and that has a maximum value that is equal to V Thevenin squared divided by 4 RL. Okay, so this is V power, whatever units you're using, and this would be then resistance RL. So indeed, if you were to go through that graphing, if you were to assume some values for the Thevenin voltage and the Thevenin resistance and then plot different values of load resistance, you'd get something like that. Okay. So this is kind of nice then. I have another page here. Yeah. Let's say that someone comes along, they give us a Thevenin model, or maybe we've had to find the Thevenin model. A lot of times, maximum power is really easy. Set the Thevenin or load resistance equal to the Thevenin resistance. All of the work is in coming up with what in the world the Thevenin resistance is. Well, let's say someone was really nice to us and they gave us the model. So we have 5 ohms here. We have 10 volts there. And we're asked maximum power. Okay. What value of resistance do we put in here for maximum power? Well, we know that this load resistor has to be equal to the Thevenin resistance, which is 5 ohms, right? So we could go back and we could get our equation here. Let me put a box, I guess we go back and use that equation where we say that V Thevenin squared divided by 4 RL, what's that going to be? And we've got 10 squared divided by 4 times 5, right? So that would be essentially 100 over 20, which gives me 5 watts. Now, like I say, I don't ever remember those things because I just come over here and I look at finding what the voltage here is. What's that voltage V? Well, it would be equal to 10 times 5 ohms divided by 5 plus 5 ohms, which gives me 5 volts, right? Or even faster, you know that because these two resistors are the same, it has to be just half of the total voltage. It has to be 5. I was just showing you where that came from, voltage division. So then I could really just say that power is equal to V squared divided by R. So we have 5 squared divided by the resistance, 5 ohms. So what do we come up with? 25 divided by 5, that must be 5 watts. Okay, so nothing wrong with remembering this. I think it's probably just easier to remember the concept that the load resistance is equal to the Thevenin resistance and then do the quick circuit analysis to get the power. Well, anyway, we've got a whole new reason to do problems, is to come up with maximum power transfer. So let's see if we can do that. I've got an example here. It's going to be kind of an ornery example. We notice right off that it's got a dependent source, so I cannot use the shortcut. And let's say that someone was asking us on this to come up with the resistance, the resistance for maximum power transfer. So find R sub L for maximum power transfer. Okay, I got off on my page numbers here. There's 2, 3, so this would be 4. Okay, so find RL for maximum power transfer. So we would like to put, what resistance could we put across here? RL for maximum power transfer. That's what I'm looking for. Well, if I look at this, it has a dependent source. Dependent source. So that's bad news, because that means no shortcut. Because if we could use the shortcut, we could just short out the voltage sources, open the current sources. Is that how we do that? We open the current sources, we short the voltage sources, and we look back into the terminals. Okay. Well, what we're going to have to do then is we're going to have to find V open circuit and I short circuit, and then we know that our Thevenin is going to be the ratio of that V open circuit to I short circuit. Okay, so let's go about doing that. Let's say that I have not put that resistor on there yet, so I would have the open circuit voltage across there. Well, maybe I'll come back to this. I'll set this aside. I've got several pages here, I think, where I put this circuit on. Yeah, okay. So we'll come back to 4. And if you're struggling with circuit analysis, these are great problems because you get a lot of practice with circuit analysis. So I would like to find here V open circuit. I'm going to flip the page and we'll find I short circuit in a little bit. But if I try and find V open circuit, what I'm going to go ahead and do is I'll talk about some currents here. Maybe I'll say that this is current 1, I1, that this is current, what will I call this, current 2, I2, and I will call this current 3, I3. I'm going to use a node technique on this. So I'm going to say that I1 plus I2 plus, because this is open, I really just have there's no current going down here, right? I is equal to 0 there. So I3 is actually the same there, so I can just say that this is equal to I3. That's equal to 0. So what's I1 going to be equal to? That's the current going like that. So I need to find the voltage opposite that. That would be minus 12. So I'll say that it's V1, the voltage up here, V1, minus 12 divided by 4K, plus I2, which is V1 over 2K, plus I3. What's I3? Well, we'll call this V naught, how about? Or V, I guess we could call it V open circuit. Yeah, I'll just call it V open circuit. There's V open circuit divided by what? 4K? Because the voltage across there is the same as the voltage across there. So we could go ahead and go through this, multiply by 4K. So I would have V1 minus 12 plus 2V1 plus V open circuit is equal to 0. And I get then that, making sure I do this right. Did I do that right? V1 minus 12, 2V1 over, yeah, and V open circuit. So how many V1s do I have? I have 3 V1 plus V open circuit is equal to 12. That's a nice equation, but it has two unknowns, V1 and V open circuit. So hopefully I can relate those. I could say that, I mean, if you talked about getting to V1, that would be the voltage across there, wouldn't it? Which would be the same. V1 is going to be equal to V open circuit, going from there to there, and then plus 2 VA. Plus 2 VA. Is that right? Go from there to there, there's V open circuit, and then I add 2 VA. That's going through that source there. Now what in the world is VA? Well, VA is the voltage across there, isn't it? That's really the opposite of this. So we note that VA is equal to, because remember I found that when I was trying to find this I1, I was finding the voltage that way, wasn't I? So VA is equal to 12 minus V1, isn't it? Okay, so I make that substitution up into there. V1 is equal to V open circuit plus 2 times VA, which is going to be 24 minus 2 times V1. So I add 2 V1 to both sides and I get 3 V1, is that right, is equal to V open circuit plus 24. And then what I would really like to do, I mean, I would like V open circuit. That's what I'm looking for. So what I want to do is I want to substitute for V1. I mean, you could substitute for whichever one you want. You're just going to have to go through more work or more time, more length to get it. So let's make our substitution smart, make a smart deal here, and say then that V1 is equal to V open circuit divided by 3 plus 24 over 3 is what, 8? So that's what V1 is. So now I'm going to substitute that into here. And I could say that 3V1, well, I guess I could have made the substitution for 3V1. That would have been even better, because I'd come right back here to V open circuit plus 24 plus V open circuit is equal to 12. So we have 2 V open circuit is equal to 12 less 24 minus 12. So V open circuit is equal to minus 6 volts. Okay, so a couple things are kind of interesting with this. It's negative. So that tells us right off, because our Thevenin is going to be equal to V open circuit divided by I short circuit. R Thevenin has to always be positive. We can't have negative resistance. So we know then that I short circuit is going to have to be negative, so we get the negative signs to cancel. The other thing about this negative is it's not a big deal when we build the model. We could do this a couple of different ways. we could put this in as positive and negative, and we call it minus 6 volts. And I think we're just looking for the load resistance for maximum power transfer, so we wouldn't necessarily need to build a model, but if we were going to, and we might for good practice, we just have this minus 6 volts, or what I oftentimes do, flip the source, positive, negative, and then we'd get to say 6 volts. Okay, so a couple of things. I'm glad that came up. Kind of in a tough problem. You have to be careful how you handle it, and probably mesh might be better on this one. You could do a mesh in here, and you could do a mesh in there. So I'm not going to go through that, but pull up a piece of paper and see if you could get this same answer here for mesh. Well, we'll continue on. And if we look at, now we're finding, what was this page was about, 5 was about finding V open circuit, right? So this is about I short circuit. So how do we get I short circuit? We short this out, don't we? Okay, so there is I short circuit. And maybe I'll use the same currents. I think I had put I1 in there. I think this was I2. And this was I3, which when we look at it, we get current coming up to this point. You got some happy current here. Is it going to go through 4K ohms resistance, or is it going to go through this dead short? Well, current, just like people, takes the path of least resistance. And no self-respecting current is going to go through 4K of resistance when it could just go through here. So this is effectively removed. And this point then essentially becomes the same as our ground reference point there. So with that, let me see what we've got here. We'll call this again V1. So I'm going to have that, is this going to be the same? I think this will be the same over here, won't it? So I could say that, what about I1 and I2? That's leaving this node, right? I1's going like that, I2's going like that, and I short circuit plus I short circuit is equal to 0. So I could say that I short circuit, if I wanted to, was equal to minus I1 minus I2. Is that right? Which would be, and we could go back to our previous work for this, we could say that this would be what we have for I1. It should be the same here. It's not going to be affected by this shorting out. I have V1 minus 12. So when I put a negative sign in front of that term, I have 12 minus V1 divided by 4K. And then I have this I2, which is going to be V1 over 2K, but I have to put a negative sign in front of it, so I'll put a negative V1 over 2K. And that's equal to I short circuit. Okay, so I'll leave that like that. I can't necessarily make a substitution for I short circuit. I don't know that I want to, because that's what I'm looking for. What I'd really like to try and do is find V1. So let's go over here and see if we can do that. This voltage here is essentially the same as ground. I mean, if this is 0 volts, this is 0 volts, isn't it? So I could say that V1 is really just equal to what? 2 VA. The voltage there is 2 VA. So V1 is going to be equal to 2 times what's VA? Well, I could say that it's, did I have that? That's, I need to go that way, so that's minus 12 plus V1, right? We've done that before. So I'll say V1 minus 12 divided by 4K. Okay, so that's the that's that current. Okay, times, I got to multiply that by 4K, right? Yeah. Okay, so does that make sense? VA, we're saying, is essentially that voltage right there. So, yeah. I've messed this up a little bit. Okay, so I'm going to back up here a little bit. I'm going to be more careful with this. I could say that VA is the voltage at A is going to be equal to minus this current here, I1. There we go, minus the current, because that current is going this way, and our polarity is negative and positive, so minus I1 times 4K. That's what that voltage is. So when I come down here, I have the 2 from up there, and then I1. Do we have I1? Well, I1 is, because this is minus I1, so I1 is just going to be positive V1 minus 12 over 4K, and then there's the 4K. So there's where that came from. There's where that came from. Now the last thing is I need this negative sign here. So I have to put that negative sign in there. So when I go through this, I can say then that V1 is equal to 2 times 12 minus V1. Well, I kind of made a big deal out about nothing there, because you could also just say, we could come over here and we could look at VA, couldn't we? VA is that arrow there. I mean, I was finding this voltage to try and define this current I1, because I wanted to find the voltage potential opposite direction of the current, but this is VA, so how do I get from there over to there? Well, I subtract V1, and add 12 to it. Is that the same thing that I have there? Because this is saying essentially VA, this is 2VA, I get back here, this is essentially VA, isn't it? And I said over here that was 12 minus V1. Yeah. So the bad news is I think I did this a more difficult way here. The good news is I got the right answer, and we can check it out there. So anyway, however you get it, whether you do this or whether you do this, hopefully you understand both of them. We now have a nice expression for V1. Well, maybe not a nice expression. Maybe I need to tidy this up. V1 is going to be equal to 24 minus 2V1. So I get, what, 3V1 is equal to 24, or V1 is equal to 8. Okay, V1 is equal to 8 volts. So when I go back over here, I'm going to substitute this in and say then that I short circuit is equal to 12 minus 8 divided by 4K minus 8 over, because I have that negative sign there, 2K, which gives me what, 12 minus 8, 4 over 4K minus 8 over 2K, which gives me 1 milliamp minus 4 milliamps, which is going to be, because this is volts over K, would give me milliamps, so I have minus 3 milliamps. Okay, that's I short circuit, and that's really good news, because what we expected it had to be a negative sign, because once our V open circuit, I'll tell you what, if V open circuit was negative and we got a positive here, we'd know there was some mistake somewhere, or vice versa. So this is good news. If we got a negative there, I got a negative there. Good. Well, so that's page 6, page 5. Let me back up to page 4. So we said that from our previous work, we found that V open circuit, what was that, minus 6 volts, and I short circuit is equal to minus 3 milliamps. So we could say then, cover sheet in here. Yep, good. So we could say then that our Thevenin is equal to V open circuit divided by I short circuit, which is minus 6 divided by minus 3 milli. Got to make sure you keep that milli in there because we're going to come up with an answer of what? Positive 2 k ohms. So if you wanted to come up with a model on this thing, the model would look like this, and I talked some about that. I'm going to flip this, say that that's that, so I can say that it's positive 6 volts. We'll put the resistor right there. That resistor we just found out to be 2 k ohms. And then the question comes up, what load resistor could I put on there to have maximum power transfer, and what would that be? That'd be 2 k ohms, wouldn't it? Okay, that'd be 2 k ohms. And you could go ahead and figure out what that power was. You essentially have 3 volts across there. You don't even have to worry about the polarity because you're going to square it. So you're going to have 3 squared divided by 2 k ohms, and you could work that out. But the important part was we found R sub L for maximum power transfer. And again, like I mentioned earlier, that's the easy part. I mean, down here we said, so RL has to be equal to 2 k ohms for max power. The difficult part was coming up with all of that. And that's good because it gives us a lot of practice. Now I think one of the trickier parts on this problem was probably V open circuit. Probably would have been easier to do with mesh analysis. I think probably I short circuit would have been easier to do with mesh analysis. So that gives you a great opportunity to try those out. And like I said, I made this look a little harder than it probably needed to be, but we got the right answer. And this would probably be a lot easier to look at there. So anyway, we've got one more lecture coming up for Norton and Thevenin. We'll do that, and then we'll have the lecture after that going into operational amplifiers. So grab a piece of paper, grab a practice problem, and see if you can work along with this. Take care till next time, and thank you for watching.